Good morning, everyone. Before we dive into the presentation, I'd like to get a feel for your background in restoration design. I believe you should have received a prompt to fill out a poll when you entered this session. You might be able to also navigate to the poll on the right-hand side of your screen. So today we're going to go through a case study on resilient restoration design from New York State. This project was performed on behalf of the New York Department of Environmental Conservation. We're going to examine the site conditions, delve into the climate change impacts, and then combine those to look at site-specific sensitivities. From there, we'll move on to adaptation measures, which were applied to increase the resilience of our site to the year 2050. If you're familiar with restoration projects, you know, unfortunately, that there are many types of failure that can occur in current conditions. We might see scour, flanking, we might see materials moving or being buried under sediment. So this is all without taking climate change into consideration. The goal of our project here is to do our best to ensure a resilient restoration that remains stable until at least the year 2050. We based our process off of guidance from the EPA, SURF, and ISI. In essence, we first reviewed the site characteristics, assessed climate projections, and then merged them to identify the portions of anticipated design that would be sensitive to climate projections. From there, we developed adaptation strategies to include in the design, as well as monitoring needed to ensure the design is performing as intended. One of the most important aspects of our project was to create an adaptation and maintenance plan. As climate science is continuing to evolve, this plan ensures that the project is able to evolve alongside it. It's intended to be a sort of living document, which can be updated as climate change projections and project specifics, such as monitoring and maintenance, are also updated. So the site we used for this case study is a Superfund site in New York State. The site was historically a metal fasteners plant with groundwater, surface water, and soil contaminated with heavy metals, specifically cadmium and trivalent chromium. To clean up the site, New York DEC removed over 40,000 cubic yards of soil and sediment from the fastener plant parcel, the non-tidal stream running south from the plant to the lake, which is outlined in blue here, and the lake itself. A future phase of work will include the tidal portion of the stream as well, which runs south from the lake to Babylon Cove at the very bottom of that map. After the removal of contaminated soil and sediments, the stream needed to be put back in place via clean fill, stone, and vegetation. As you can see, it's a quite constrained environment. The stream and lake are both tightly bound horizontally by the neighborhood and the school, making stability a high priority of this restoration. Unfortunately, this isn't a restoration project where we will able to do a lot of habitat improvements, add in stream meanders or floodplain connection. It's more of a protection-based restoration. Climate change impacts obviously have already been observed in the Chesapeake Bay Watershed, and these trends are expected to continue. To ensure an enduring restoration design, we reviewed climate change projections for the project location. New York State was a great state to do climate work in, as there's region-specific climate data, such as this New York CERTA report. The projections that they use in this report are based upon greenhouse gas concentration pathways, which are modeled on variable emission scenarios. I'm going to go through projections rather quickly. I think we all kind of have an idea of what is going on. Temperatures are getting hotter, storms are getting worse, but we'll go through the specifics here. The middle range projection for this area of New York shows a temperature increase of about 6 to 10 degrees Fahrenheit by the year 2010. You can see in the graph here the projection period and the percentile change expected, with the 10th being that gold line on the bottom and the 90th percentile being the purple on the top. we're focusing primarily on the central range with some of the high projections, the 90th percentile included, just to get an idea of the worst case scenario. So in general, summers are going to be hotter and winters will be more mild. Potential impacts would be lower dissolved oxygen, increased surface water temperatures, release of excess nutrients, increased chemical reactions, and changes in circulation patterns in the tidal zone. In the Chesapeake Bay region, precipitation and sea level rise appear to be the most worrisome factors looking forward. For our project area specifically, the middle range emission scenario shows a 19% increase in precipitation by the year 2010. Heavy rainfall events greater than 1 inch per day are modeled at a 31% increase. The graph shown on this slide was produced by the Northeast Regional Climate Center and shows the current 100-year return period is expected to equate to the 40 to 50 return period by the year 2070. The impacts of more and heavier rain are substantial, and they include increased erosion, decreased water quality, and increased mobilization of contaminants. When we started this project, the finest scale available precipitation data was that New York SERTA climate change report, which had region-specific precipitation modeling. To get a finer scaled future hydrology data for this project, we performed downscaling. We wanted to use a historical event that exceeded the existing conditions 100-year recurrence interval peak. So we decided to use stage data from the largest recent storm event, which was Hurricane Sandy in January of 2012. This was an approximation only, and it has several unknowns, including wind data. Since we performed the downscaling, the Mid-Atlantic Regional Integrated Science and Assessments Program, also known as MRISA, published an IDF curve tool which can be used for projected future hydrology at the project scale. This is a super awesome tool, and I highly encourage you to check out the Chesapeake Stormwater Network webinar, which has a lot of data on the tool background and how to use it and apply it to your specific project. Looking at the stage hydrograph here on the right-hand side of the screen, you can see that the storm surge at this site is slow. It occurs over many hours. This compiled with the slope of our stream means that there are not too many high velocity or shear stress values at our stream, but that flooding impacts can be substantial. Moving on to sea level rise, as with other climate change variables, we provided a range using mean higher high water as the base level. If you're not familiar with the tides in this area, there are 2 low tides and 2 high tides each day. We're using the highest of the high tides, mean higher high water. So in our range of projections, we're using 2 for the most part. Mid is the 50% probability that sea level rise meets or exceeds this level. This is the most probable projection. We're also using the high projection, which is a 1% probability that it will meet or exceed that level. And this is good for that worst case scenario. In addition to sea level rise itself, we're using major flood stage from storm events. So we took the mean higher high water elevation currently from the nearest NOAA tide station. We then added the projected sea level rise for both 2050 and 2010 in both the mid and high level projections. That's the 50% and 1% exceedance. We also looked at the existing conditions major storm surge from the National Weather Service and added this to the projected sea level rise. In addition, we can expect major storms to increase in magnitude over the years. So we also used Hurricane Sandy as an approximation of projected storm surge to get a potential worst case scenario. Looking at a visual representation of the current conditions at the site, let me get a tool. Okay. We have the current mean sea level at 0 feet. The current mean higher high water elevation for our project is at 0.6 feet. The historic Sandy flood stage is 7.1 feet above mean higher high water. So we will add the 0.6 to 7.1 to get a final stage of 7.7. If we compare this to the projected sea level rise values, they range from 1.9 to 6.6 feet. This is within the Sandy footprint. While the range of sea level rise plus existing major storm surge is from 6 to 10.7. This well exceeds Sandy. If we go a step further and add sea level rise to the potential future storm surge, even the lowest end of the range exceeds Sandy at 9.6 to 14.3 feet. When we overlay this, let me get to my mouse. When we overlay this on the map of the project area, you can see the extent of the projected flooding for the range of scenarios. This first slide here shows existing conditions with the current major storm stage in light blue and the Sandy projected storm stage in dark blue. As this site is in current conditions, flooding events impact the tidal portion of the stream with potential impact within the lake and upstream. By the year 2050, in the mid-range projections, mean higher high water would exceed the lake control structure. With major events, inundation would extend up past the lake into the non-tidal stream and up to this local high school. These impacts would extend both east and west of the lake. In 2050, the high range projection mean higher high water increase due to sea level rise is now visible on the map in the lightest shade of blue. You can see it here and here and here. The lake would be affected during the existing conditions major storm level, not just the potential future storm based on Sandy. As we can see here, the 2010 mid-range projections are quite similar to the high-range projections for 2050. Finally, the 2010 high-range projection, the inland flooding extends to the upper portion of the non-tidal stream. The lightest blue, indicating mean higher high water, floods the entire coast and associated infrastructure, as well as most of the lake shoreline. We get some flooding even north of the highway that separates these neighborhoods. With these potentially high impact climate change scenarios in mind, there's a long list of sensitivities at our site. The higher priority impacts and effects on the non-tidal portion of the stream include altered precipitation pattern, which could cause more intense flooding, storms, and runoff. Looking longer term, sea level rise could have serious impacts on all three habitats of the project, including the non-tidal, lacustrine, and tidal. Effects we may see there include site inundation, increase in erosive forces, and mobilization of contaminants. Finally, the increase in temperature has a negative effect on plants and animals living in the project area. To provide adaptation measures, we want to go through an iterative process of design. As part of this, we need to identify thresholds of climate impacts. These thresholds should be something measurable. So for example, if we don't have a stream gauge at our site, we wouldn't set a discharge threshold. We want easy to measure thresholds at our project. So those for us were temperature over a certain degree Fahrenheit using temperature gauges, rainfall over a certain number of inches in a 24-hour period using rain gauges, and storm surge over a certain elevation. And for that, we use the NOAA gauge. The thresholds are set at quantities we believe would provide the substantial impact to the design. Staff would then monitor these thresholds to see if they're exceeded, and then have an action plan in place to remediate any impact to the design if necessary. Monitoring would then be performed to review the success of our adaptation actions, and the process would restart with new site characterizations and then identification of a new set of thresholds, etc. Adaptation strategies roughly fall into 3 categories. We have resistance, resilience, and response. Resistance is often the first reaction a community or project will have, and it's a protection-based strategy. Resistance could be something that armors against climate change impacts, like a seawall. In a restoration project, this could be riprap along the side of a stream. Resilience, on the other hand, is an approach where you provide adjustment to the impacts. This could often include putting a structure on pilings to elevate it above sea level, while allowing the seawaters to extend into the project area safely. In a stream restoration project, this could be providing floodplain access to reduce erosive flows. Finally, the response is the least favorable option to most communities and projects. This might include managed retreat of a community or project from the sea level zone. This could also include full removal of contaminants from a site out of that zone. At our project, we put into place a combination of resistance, resilience, and response strategies to protect against a range of climate change scenarios. So a few more examples of resistance and resilience strategies for restoration projects specifically may include sizing structures and stones for larger design storms. For this, you would need that detailed site-specific hydrology and hydraulics. It could also include soil reduction, which could be done through the creation of floodplain wetlands. This may also include alkaline soil treatments, specifically if you have contaminants that you don't want experiencing an increase in pH. And landscaping temperature modifications. This could be adding more tree canopy to your site. Resilience would include making your plant species resilient to the changing climate. In the summertime, this would mean you need plants that are resilient to high temperatures and drought conditions. In the winter, this could be plants that are able to accommodate increase in floods and inundation. We also want to make sure we're doing monitoring at all times. That's, I think, our biggest protection measure. To provide resilient restoration, we recommend establishing a formal climate adaptation plan immediately. This provides thresholds and actions for the project. Longer term, we recommend continuing monitoring, which enables checking threshold levels and implementing adaptation measures. Keep an eye out always for developing data, tools, and technologies. Who knows what will be in 10 or 20 years? And finally, consider adaptation measures in conjunction with regional planning. The most efficient and effective way to prevent inundation impacts is for projects and communities to work together on a master plan. Thank you so much for attending the talk today. If you have any questions, comments, or suggestions, please reach out to me. I would love to hear what you have to think.